right, so let's start with a review of where we left off last time. Okay. All right. So last time we were in section 1.1. We began our introduction to propositional logic. We discussed what a proposition is. Okay. We talked about truth values and truth tables. We also discussed negations of propositions, as well as conjunctions. We said a conjunction of two propositions is when we combine them with the word and. So we have a question, just one moment, let me just finish going over this. Okay. We talked about disjunctions. All right. Written that way, that's when we combine two propositions with the word or. And we also discussed conditional statements. Okay. Denoted this way, a conditional statement is a sentence in the form if P then Q. All right. For all of them, we discussed when they're true and when they're false. So you need to know that when conjunctions, disjunctions, and conditional statements, when all of them are true, as well as for negations, and when they're false. Okay. So remember, we said that a conjunction will be true only when both of its parts are true. Disjunctions will be true when at least one of its parts are true. And conditional statements are only false when the hypothesis P is true, but the conclusion Q is false. All right. And we also gave a couple of alternative ways of writing conditional statements in English. Okay. All right. All right, so to answer your question, do you have to memorize truth tables? You don't have to memorize the truth tables, but you have to know when each of these types of compound propositions are true and when they're false. Okay. There wasn't any homework yet. No, I plan to give you your first homework after today's class. All right. Okay. Any other questions? Okay. Any other questions about anything from last time that anyone wanted to ask or go over? Okay. All right, so let's begin. We're going to continue where we left off. We are still in section 1.1 for now. Okay. So again, the last thing we were discussing was conditional statements. We're now going to define what the inverse, the converse, and the contrapositive are of a conditional statement. Okay, so we are now continuing. So definition. First of all, we're going to define what the converse of a conditional statement is. So the converse of the conditional statement if P then Q is the proposition if Q then P. Okay, so the converse of a conditional statement is where we basically switch the hypothesis and the conclusion. Okay. The inverse of the conditional statement if P then Q is the proposition if not P then not Q. Okay, so it's where we negate the hypothesis and the conclusion. Okay, so the converse and the inverse, when we write the converse or the inverse of the conditional statement, we've created a new proposition. It's a different proposition that will have different truth values, right? If we were to write out the truth table, we would see they would have different truth values. Third is the contrapositive. The contrapositive of the conditional statement if P then Q is the proposition if not Q then not P. Okay, so it's where it's both the converse and the inverse. It's where we do both. We switch the Q and the P and we negate them both. Okay. Okay, so for example, let's say we had a proposition as follows. A proposition, let's say, is the sentence, if I have a flat tire, then I will be late for class. Okay, so this is a conditional statement here. All right. Okay. In this sentence that I've written, P is the sentence I have a flat tire. Okay, that's P. Q is the sentence I will be late for class. Okay, that's the P and that's the Q. Okay, the if and the then are not part of the P and the Q. That's represented by the arrow. Okay. All right, so what would be the converse of this sentence? Okay, the converse is a new proposition. That's the proposition if Q then P. Okay, that would be the sentence. So again, we're switching the hypothesis and the conclusion. So that would be the proposition if I will be late for class, or if I am late for class. I'm not usually so strict on the tenses. Sometimes we need to play with the tenses a little bit to make the sentence sound better. So if it sounds a little awkward sometimes, I apologize, but let's write the converse here. If I will be late for class, then I have a flat tire. Okay, so that's the converse there. We switch the two. The inverse of this sentence would be the sentence if not P, then not Q. Okay, where we don't switch them, we just negate them. So that would be the sentence if I do not have a flat tire, then I will not be late for class. And the contrapositive of this sentence is where we do both. So that's if not Q, then not P. So that would be the sentence if I will not be late for class, or if I am not late for class, then I do not have a flat tire. Okay, now from all of these three sentences here, the converse, the inverse, and the contrapositive, okay, only the contrapositive will have the same truth values as the original sentence if we write out a truth table, which we'll do in a minute, okay? So only the contrapositive will have the same truth values, which tells us really that only the contrapositive is the same sentence as the original sentence, okay? So let me write that out here. That's actually what we call logical equivalence. Okay, so let me give you the definition for that, and then we'll write out the truth table for all of these. So when two compound propositions always have the same truth value, we call them equivalent or logically equivalent. Okay, so again, if I have two compound propositions, all right, and when one is true, the other one is always true. When one is false, the other one is also false. So they always have the same truth value. They're always true in the same cases, okay? Then those two sentences are basically the same sentence, okay? They mean the same thing, so we call them logically equivalent, okay? So we're going to demonstrate that now with these conditional statements here, okay? So we're going to write out a truth table for a conditional statement, its converse, its inverse, and its contrapositive. Okay, so I'm starting with P and Q, not P and not Q, okay? All right, then I'm gonna write down the conditional statement if P then Q. Next, I'm gonna write down its converse, if Q then P. Then its inverse, if not P then not Q. And then finally the contrapositive. If not Q, then not P. Okay. All right, we have two variables here, P and Q, are four possibilities. So for P, I write true, true, false, false, true, false, true, false. Right, for not P, negations always have the opposite truth value of the original proposition. So if P is true, not P is false. If P is false, not P will be true. Okay. Same thing for not Q, opposite truth value, so it's going to be false, true, false, true. Okay. So here's our conditional statement, if P then Q. Okay, remember, conditional statements are only false when the hypothesis is true, but the conclusion is false. So we have here our hypothesis is P. Our conclusion is Q. So I look at P and Q. I see in the first row here I have true, true, so that's true. In the second row I have true, false. P is true, Q is false, so the statement would be a false statement. If P is false, Q is true, that's the third row. The conditional statement is true. If P is a false statement and Q is also a false statement, the fourth row, then the conditional statement will be true. Okay. Let's move on to the converse now, okay? For the converse now, Q is my hypothesis, P is my conclusion, right? The hypothesis and the conclusion have switched. So looking at P and Q, first row, Q, the hypothesis is true, P, the conclusion is also true, so the statement is true. Next row, my hypothesis Q is false, the conclusion P is true, false, true, it's a true statement. Okay. Third row, my hypothesis is true, the conclusion is false. That's when the conditional statement is false. And final one, false, false, it's true. Okay. Let's move on to the inverse. Okay. So here my hypothesis is not P. My conclusion is not Q. So I look at not P and not Q. Okay, here's not P. Here's not Q. Okay. So here in the first row, they're both false, so the statement is true. In the second row, the hypothesis not P is false, the conclusion is true, so that's true. Okay. Next row, not P, the hypothesis is true, not Q is false. False, whenever I have true, false, it's false. And the last one, they're both true, so the statement will be a true statement in that case. Okay. So the only time, if not P, then not Q, the inverse, the only time that statement will be false is when not P is a true statement and not Q is a false statement.
Professor, I have a question.
Yes, go ahead.
I thought is the negation for P then Q, I thought it was supposed to be like false, true, false, false, because you're looking at what's that? The fifth column. So I thought it was supposed to be like the opposite of that column.
Which one? What are you? Go over that again. I'm sorry if you could repeat that.
So the inverse one, where you have
yes,
negation P then negation Q.
Yes.
Compare it to the P then Q.
I see. I see.
Are you
compared to this one, the fifth one you said,
yes,
right?
The fifth one, yes.
Okay, that's an excellent point. I was gonna bring that up in a minute, but since you mentioned it, let me discuss it now. Okay. So his question is, shouldn't the inverse here, shouldn't this column, this inverse column, shouldn't that just be the negation of this column, the negation of the original proposition here, right? If P then Q. So the answer is no. And let me sort of discuss that now, okay? The negation of that proposition would be this, would look like that. Not if P then Q. That's the negation, okay? The negation symbol does not distribute. So this is not the same thing. We write it this way. This is not the same thing as saying if not P, then not Q. They mean two different things. They're two different sentences, okay? And we could demonstrate that using a truth table. In fact, we can do that in a moment if you like, okay? All right, so those two things are not the same. The negation there would not distribute, right? All right. Any other questions on that? I hope that answered your question there.
Yes, it did.
Okay. Okay. All right. Also, when we're doing this, you have to be careful to keep in mind what's the hypothesis and what's the conclusion. Okay. A hypothesis is always the if part of the sentence, what comes before the arrow. The conclusion is the then part. That's what comes after the arrow. Okay. All right. Okay. Let's move on to the contrapositive now. All right. For the contrapositive, the hypothesis is not Q. The conclusion is not P. Okay. So we go to not Q and not P. We get false, false, true, true, false, 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 true, 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 true. Okay. All right. So looking at all of these four conditional statements here, we have our original conditional statement, if P then Q, and its truth values, right? When it's true and when it's false. Okay. If we look at the contrapositive, okay, we'll see only the contrapositive, as I said before, has the same truth values as the original, right? They're always the same. Wherever one is true, the other is true. Wherever one is false, the other is false, okay? So when that happens, that tells us, as I said, that the two propositions are logically equivalent, or in other words, they're basically the same sentence said in two different ways, okay? They're equivalent to each other. So the way we would write that is with a triple equal sign. So if the conditional statement, if P then Q, is equivalent to, logically equivalent to its contrapositive. If not Q, then not P, okay? So this symbol here means logically equivalent. Okay. All right, and again, anytime two propositions are logically equivalent, we know that they will always have the same truth values. So if one is true, so will the other. Okay. That's an excellent point. As somebody just pointed out, the converse and the inverse, while they're not logically equivalent to our original proposition, they are logically equivalent to each other. Okay. Right, the converse and the inverse are logically equivalent. Not only are they logically equivalent to each other, but they are actually contrapositives of each other. Right? If you look at the converse is if Q then P. Okay. If you switch the Q and the P and negate them, you get the contrapositive, which is the inverse. If not P, then not Q. Okay. Okay. Any other questions on that? Yes, this is being recorded. This will be up later on Blackboard. The converse and inverse, they are logically equivalent to each other. Yes. So so the converse and inverse are logically equivalent to each other. Okay, they're just not logically equivalent to the original statement. Okay. Okay, good. Any other questions? Yes, anytime you have any conditional statement and you write down its contrapositive, the contrapositive will be logically equivalent to your statement. Okay, for any conditional statement. Take any conditional statement, you write down its contrapositive, it will be logically equivalent. Okay. Any other questions? Oh, excellent question. Right now, we're sort of right now we're sort of breaking down language. If you want to plug in language into a computer, first of all, you need to break it down in a way that the computer can understand. So there has to be rules. Okay. So that's one application of this. All right. So they sort of give rules to language so that the computer can understand what you're telling it. The second application is we're going to eventually get to proofs, to mathematical proofs. All right. So in order to develop our techniques for proving things, we're going to use logic. We're going to break down when sentences are true and when they're false, and then we'll be able to prove when certain sentences are true and when they're false. Okay. Any other questions? Okay. All right, so let's now move on to the next type of compound proposition. We're now going to discuss biconditional statements. Okay. Okay. All right, so let P and Q be propositions. The biconditional statement denoted by this symbol here, a P followed by an arrow pointing both ways, followed by a Q, is the proposition P if and only if Q. Okay, so any sentence of this form, P if and only if Q, is a proposition, and it's called a biconditional statement. Okay. Biconditional statements are true when P and Q have the same truth value, and they're false otherwise. Okay, so P if and only if Q is true when P and Q have the same truth value. Or have the same truth values. And is false otherwise. Okay. So what a biconditional statement says, if you have any sentence that's a biconditional statement, it's saying, basically what it's saying is that if P is Q, if P is true, then Q is true, and if Q is true, then P is true. It's saying when one is true, so is the other. When one is false, so is the other. That's sort of what a biconditional statement is saying. Okay, so biconditional statements are true when P and Q have the same truth value, and the false otherwise. All right. So let me give you the truth table for biconditional statements. Okay. All right, 2 variables, 4 possibilities. Okay. In our first row here, P and Q have the same truth value, so the biconditional statement would be true in that case. If, let's say, P is true but Q is false, so then they have 2 different truth values, so a biconditional statement would be false in that case. Third row here, P is false, Q is true. Those are different truth values, so the statement would be false. And final one, P is false, Q is false. They have the same truth value, so again, the biconditional statement would be true. Okay. All right, so to understand this a little bit more, let's maybe see an example of an actual sentence that's a biconditional statement. Okay. All right, so let's say we have a proposition P. P is the proposition, you can take the flight. Q is the proposition, you buy a ticket. You buy a ticket or you bought a ticket. Okay. So we can create from these 2 propositions a biconditional statement, P if and only if Q. That would be the sentence, you can take the flight if and only if you buy a ticket. Okay, so let's sort of try and understand the truth table we wrote above. Like, when will this statement be true and when will it be false? Okay, so let's go to the first case from the truth table where both P and Q are true. Okay. So if P is true, that means you can take the flight. That's true. And let's say Q is also true. You bought a ticket. Okay. So remember, in order to think about whether this statement is true or false, we're trying to figure out if it's a lie or not. Okay. So let's say you buy a ticket and you're also able to take the flight. P and Q are both true. So the statement is true, right? I told you you can take the flight if and only if you buy a ticket. You bought a ticket and you can take the flight. So it was a true sentence. Okay, it wasn't a lie. All right. Let's go on to the second case, all right, where P is true, but Q is false. Okay. So in that case, that means you can take the flight, but you did not buy a ticket. All right. So I told you, or the airline told you, you can take the flight if and only if you buy a ticket. Okay. And you can take the flight, P is true, but you did not buy a ticket. Right? I don't know. Let's say you had miles. You used your miles. You did not end up buying a ticket. Okay. In that case, this sentence is a lie. I told you could only take the flight if you bought a ticket, and you're taking the flight without buying a ticket. So this statement is a false statement. Okay. The third case, P is false, Q is true. Okay. In that case, so you cannot take the flight, but you bought a ticket, right? So the airline told you you can take the flight if and only if you buy a ticket, right? So you bought a ticket, and then they told you that they overbooked the flight, then you get bumped, so you can't take the flight. All right. So that means the airline lied to you. You bought the ticket, Q is true, but you can't take the flight. P is false. So this statement is a false statement. Okay. And hopefully it wasn't United. Otherwise, they might have beaten you up on the way out. But anyways, the final one here. All right, P and Q, let's say they're both false. Okay, so the airline told you you can take the flight if and only if you buy a ticket. Let's say both of those are false. So P is false, you can't take the flight, and Q is false, you did not buy a ticket. So the airline didn't lie to you. You didn't buy a ticket, so you couldn't take the flight. So the statement is still a true statement. Okay. All right, so any questions on that? No. So somebody asked here, Is only if the same thing as if and only if? No. If you see the words only if, that's a conditional statement. That was one of the alternative ways of saying a conditional statement I gave you last time. If you see the words if and only if, then it's biconditional. Okay. Oh, yeah, I can scroll back. Sure. Okay. All right, so when you see the words only if, okay, you're saying one thing implies the other. When you say if and only if, that means both ways. It means one implies P implies Q and Q implies P. Is it safe to assume a truth value of false means negation? Not necessarily. You could have something without being negated that's false. For example, the sun rises in the west. That doesn't have a negation, but that's false. Okay. Okay. Any other questions? Okay. All right. In English, just like biconditional statements, biconditional statements also have alternative ways of being expressed. Okay. So let me give you a couple of those alternative ways now. So some common ways of expressing P if and only if Q. Okay, so biconditional statements. So number one is the way I already told you, P if and only if Q. Okay. By the way, as a shorthand, a lot of times I write if and only if as IFF. P if and only if Q. So IFF means if and only if. Okay. If and only if. Number two, another way of saying a biconditional statement, or of saying P if and only if Q, is to say P is necessary and sufficient for Q. Okay, and the third way is to say if P then Q, and conversely, if Q then P. Okay. Do you have to memorize this list? For the biconditional statements, I would suggest you know the different ways of saying a biconditional statement. There's not that many, and it's good to know them. Okay. Okay. Somebody's asking about the P only if Q. Why is that the same thing as saying if P then Q? I assume that's your question. We can go over that for a moment. Okay. Let me just do one more thing first before that. Okay. All right, I want to mention something briefly. 1 second. Yeah. I'll go over that. Just give me one moment. I want to briefly mention something. So I want to briefly mention something to you. We're not going to really do much with it in this class. We're not going to go over it so much. I'm not going to test you on it, but I just want to make sure you've seen it. Okay. So I'm going to give you a definition for what's known as the exclusive OR. Okay. Last time we went over the disjunction, which is also known as the inclusive OR. Remember, we said if I have a disjunction, right? That's the same thing as saying P or Q, and I told you it means or both, okay? If I want to say just P or Q, but not both, so that OR is called the exclusive OR, okay? And that's the definition I'm going to give you now. But again, I'm not going to really do much with this. Again, I just want you to have seen it. Right? So let P and Q be propositions. The exclusive OR of P and Q, denoted by this symbol here, okay, is the proposition P or Q, but not both. Okay, it's true when exactly one of P and Q is true. And is false otherwise. We had a question here, 1 second. Oh, okay, give me 1 second, I'll scroll up in a moment. Okay. All right. Okay. Excellent. Okay, so somebody was asking in the comment section, last time we said for conditional statements, if I have a conditional statement, if P then Q, so there are a couple of different ways you could express this in English. The common way, the standard way, is to say if P then Q. Okay, we said another way of saying this in English would be to write it as P only if Q. Okay, so these two things in English mean the same thing. If I have a sentence like this, P only if Q, in this sentence, the P is the hypothesis and the Q is the conclusion. Okay, and that's the same thing as saying if P, then Q. Okay, so maybe to demonstrate, let me first start by trying to demonstrate that they're equivalent with an example. Let's start with that. Okay, let's say I have the sentence. The following sentence, if P then Q, it's a conditional statement. Let's say I have the sentence, well, here, let me write it this way. Let's say P is the sentence, is the proposition, I am alive. And Q is the proposition, I have a heart. So the conditional statement, if P then Q, if I write that as an English sentence the first way, in the standard way, if P then Q, would be the sentence, if I am alive, then I have a heart. Okay. Okay, so far you're with me, I hope. Any questions so far? Okay. Now, hopefully you also would agree with me. If I were to write the contrapositive, not the contrapositive, the converse of this thing, that would be a different sentence, right? If I am alive, then I have a heart. That's a true sentence, right? If you're alive, you got to have a heart, okay? So there's a cause and effect relationship here. I know if one thing is true, the other thing also has to be true, right? If I am alive, then I have to have a heart, okay? If I switch this around, it's not necessarily true, right? If I write the converse would be the sentence, if I have a heart, then I am alive. That's not necessarily true. You know, a person after he's if a person is dead could still have a heart, right? Okay. Right. So the converse again of this is not necessarily true. All right. So I start with that. Now let's write this in the other form. P only if Q. Okay. So P only if Q would be the sentence, I am alive only if I have a heart. Right. So hopefully looking at these two sentences, you see that they're the same. Okay. I am alive only if I have a heart, right? If you don't have a heart, then you can't be alive, right? And that's the same thing that the first sentence is saying. If I'm alive, then I have a heart, right? What was its contrapositive? The contrapositive is the sentence, if I don't have a heart, then I'm not alive, which is the same thing. They're equivalent, okay? If I were to write this the other way, let's say I were to write this as, I have a heart only if I'm alive. Okay, so these two are equivalent, right? They're the same. It's not the same as this one. I have a heart only if I'm alive. That's not true. As we said before, dead people also have hearts, okay? So while the first two are the same, if I switch the order, it's no longer the same. Okay, again, in order to sort of see it, you have to try and look at the cause and effect relationship. One, if I write a conditional statement, I'm saying that when one is true, when the first thing, the hypothesis is true, the conclusion also has to be true. Okay? But the reverse is not necessarily so. Just because the conclusion is true doesn't mean that the hypothesis has to be true. Okay, so when I write P only if Q, again, I'm saying that P will be true only if, let me reverse that. I'm saying that P cannot be true when Q is not true, okay? That is the meaning the statement will be false if P is true, but Q is false, which is again, the same truth value for the conditional statement if P then Q, right? Meaning the same case where it will be false. Okay. All right, so that's sort of a mini explanation of that. Okay. Okay. I hope I didn't confuse you any more than you were confused before. Okay. All right. Okay, good. Okay. You can take any two propositions and transform them into a conditional statement. You can combine them with the words if then and make them into a conditional statement, right? It's got to have that relationship, that cause and effect relationship. So it's either got to have the words if then, or it's got to be equivalent to that in some way, okay, for it to be conditional. Right, doesn't necessarily have to be, a conditional statement doesn't necessarily have to make sense. It could be completely nonsensical. Okay. All right. Should you stick to this example? If this example helps you to sort of remember, yeah, you can always come back to this example with P and Q being the person being alive and having a heart. Okay, if that helps you. This example works. If you want to come up with something else that works better for you, that's fine as well. Sometimes in different cases, different examples might help you better. Okay. All right. So I want to now discuss writing truth tables for compound propositions. Okay. So let's do this with an example. Let's say I asked you to construct the truth table of the compound proposition So here is a bit of a complex proposition here. Our proposition is the statement P or not Q implies P and Q. Okay, so I'm asking you to make a truth table for this compound proposition here. Okay, one of the advantages of having a truth table is that it tells us under what circumstances will this statement be true, and under what circumstances the statement will be false, right? For what truth values of P and Q. Okay, so here we have a conditional statement, right? Here our hypothesis is P or not Q. That's the hypothesis that comes before the arrow, and our conclusion is P and Q. Okay, so we have a conditional statement that's got complicated parts. Okay, if I want to make a truth table for this, I always start with my variables, in this case P and Q. All right, once I have my variables, we build up the parts. So first I start with the variables P and Q. Next, on your truth table, you want to put the negations of variables, if you have any negated variables. We have here a negated Q, we have not Q, so I'll put that. I don't have any not P, so there's no point in putting that on the truth table. Okay. Next, I can build up P or not Q. I've got all the parts for that. I have P, I have not Q, so I can put the disjunction. Okay. I've also got P and Q, so I can put that. Okay. Now that I have both the hypothesis and the conclusion on my table, I can write the entire statement. So P or not Q implies P and Q. Okay, so whenever you're building a truth table, you always start with the smallest pieces and build up. I keep adding one thing at a time. Okay. All right. So we start, as always, for P, true, true, false, false. For Q, true, false, true, false. Not Q is the opposite of Q, so false, true, true. Okay. P or not Q, so that's a disjunction. That's only false when both parts are false. Okay, so we look at P, we look at not Q. P, not Q. The first row, we've got true, false. One of them is true. It's true. Next row, both are true, true. Next row, both are false, false. Last row, one is true, true. We move on to the next, P and Q. Okay. Conjunction, it's only true when both are true. So first row, true, 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 false, false. False, 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 false. Sorry. True, false. False, false, true, false, 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 false. Okay. All right. Finally, we have our conditional statement. So again, here's our hypothesis. Here's our conclusion. Okay. Conditional statements, again, are only false when the hypothesis is true, but the conclusion is false. Okay. So first row, true, 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 false. False, 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 true, true, false. False, excuse me. Okay. Okay. So what does this truth table tell me? It tells us that for this compound proposition, P or not Q implies P and Q. We now know when it will be true and when it will be false. It will be true when P and Q are both true, or when P is false but Q is true. Okay, and it will be false in the other two cases. Okay. Any questions on that? That's P or not Q. It's a disjunction. That's why it's true. Okay, as long as one of them is true, it's true. Okay. Is the structure always like this? More or less, pretty much, yeah. Can I repeat the last column? Oh, sure. Okay, so let's go over the last column again. So here my hypothesis is P or not Q. The conclusion is P and Q. So I look over at those two. For the first row, it's true, true, so it's true. Okay. Again, conditional statements are only false when the hypothesis is true, but the conclusion is false. So if we move on to the next one, I get hypothesis is true, conclusion is false. My sentence is false. Okay. All right. Again, remember, what is a conditional statement saying? It's saying that if P is true, then Q has to be true. Okay. So if P is true, if the hypothesis is true, I use P and Q. Let me use hypothesis and conclusion. Conditional statement says that when the hypothesis is true, the conclusion must also be true. So if the hypothesis is true and the conclusion is false, then that statement I just told you is false. It's a lie. Okay. Next one. False, false, true. Last one, again, the hypothesis is true. The conclusion is false. The sentence is false. Yes, I plan to give you your first homework assignment after today's class. Okay. Okay. All right, let's move on now to the next definition that I want to give you, okay? Okay. So first, a bit. A bit is a symbol with two possible values. Right, namely, 0 and 1. All right. Right, so in computer science, and somebody actually was mentioning this a little earlier in the chat, we deal with zeros and ones. Everything in computers is in zeros and ones. So 0 and 1, they're called bits. A 0 is a bit and a 1 is a bit. Okay. A bit string is a sequence of 0 or more bits. All right, the length of this string is the number of bits in the string. And so, for example, let me give you an example of a bit string. So again, a bit string is just a sequence of zeros and ones. So that would be an example of a bit string. All right, and its length is the number of bits that it has. So 1, 2, 3, 4, 5, 6, 7. This is a bit string of length 7. All right, so I'm just giving you these definitions in case you see these terms used in the homework. Okay, any questions on that? We're counting the zeros and the ones, right? Do I recommend you read the book? If you want, you can also read the book. I think the lectures and the homework problems should be enough. But if you want to supplement your knowledge with by reading the chapters, that's fine as well. Okay, that's always a plus. Okay. Okay. Yes. In other words, yes. You could think of bit as another term for binary. Bit is a contraction of the words binary digit, right? Okay, we're still in 1.1. Okay. All right. Meaning when I said it's a sequence of 0 or more bits, meaning the number of bits in the string, I meant, right? So here this would be 1 bit, this would be 0, 1 is 2 bits, 1, 0, 1 is 3 bits, and so on and so forth. Okay. 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 All right. I want to now practice writing sentences using logic symbols and vice versa, taking symbols from logic and writing them as English sentences. Okay, so this is sort of going to be a crossover between chapters 1.1 and 1.2. Okay, so let's start here with an example. Okay, all right, so let P and Q be the propositions. Let's say P is the proposition, I bought a lottery ticket. And Q is the proposition, I won the jackpot. Okay. Let's express each of the following propositions as an English sentence. Okay. So let's start with part A. Okay. So let's say I asked you to write down the sentence, this sentence here. P, if and only if Q. Okay. So using these propositions, that would be the sentence, I bought a lottery ticket. If and only if I won the jackpot. Right? Okay. Right, and then let's do another example. Let's say I asked you to write down not P implies not Q. So that would be the sentence, if I did not win the jackpot. Excuse me, if I did not buy a lottery ticket, my apologies. then I did not win the jackpot. All right, and we can combine these in several different ways. All right, generally doing it this way, going from a logical expression to an English sentence is a little bit simpler. Let's try the reverse. Let me give you a sentence in English, and let's try and write it as an expression in logic, okay, using symbols from logic. So let's try another example here. Okay. Let's say P is the proposition. You drive over 65 miles per hour. MPH is short for miles per hour, okay? Let's say Q is the proposition. You get a speeding ticket. Okay. So for this example, we're going to write down the following propositions. So write down the following propositions using P and Q and logical connectives. By logical connectives, I mean the conjunction, the disjunction symbol, the negation symbol, the conditional statement symbol, and biconditional statement symbol. Okay, so we're going to use all of those symbols and P and Q to express the following English sentences. Okay. All right, so the first one is, let's say I give you the sentence, you don't drive over 65 miles per hour. Okay, so how would you express that in logic? Yeah, exactly. That's just not P, okay? So that's not P, the negation of P, right? It's not the case that you drive over 65 miles per hour. Okay, let's move on to the next one. Let's say I give you the sentence, you drive over 65 miles per hour, but you don't get a speeding ticket. Okay. How would we express this one using our logic symbols? Yeah, okay. So this one, remember, the word but is usually used to mean and. So that's conjunction, okay? You drive over 65 miles per hour, that's P. You don't get a speeding ticket, that is not Q. So this is P and not Q. Okay, so that would be our answer. Okay, let's move on to the next example here. Okay, what about the sentence, you will get a speeding ticket if you drive over 65 miles per hour? How would you express that one? Yep, that's P implies Q, okay? Here we have the word if, right? Whenever we see if, that tells us that this is a conditional statement, okay? What's the hypothesis and what's the conclusion? The hypothesis is whatever comes after the word if. So this stuff here, the hypothesis, that's the P, that's the hypothesis. And whatever the other part is the conclusion. So this is Q, and that's the conclusion. Okay. So this, as a logic expression, would be if P, then Q. Okay, right? It's the same thing as saying, if you drive over 65 miles per hour, you will get a speeding ticket. Okay. Let's try the next one. All right. Here is the sentence. If you don't drive over 65 miles per hour, then you will not get a speeding ticket. Okay. All right, so this is in the standard if-then form, so this is clearly a conditional statement, okay? The hypothesis is the sentence, you don't drive over 65 miles per hour. That's the sentence, not P. And you will not get a speeding ticket. That's not Q. So this is if not P, then not Q. Yeah, exactly like you guys said in the chat here. Okay. Okay. All right, what about the following sentence? Driving over 65 miles per hour is sufficient for getting a speeding ticket. Okay. All right, so when I have the word sufficient alone, or if I have the word necessary alone, then it's a conditional statement, okay? So remember from our alternative ways of saying conditional statements, right? If P then Q is the same thing as saying P is sufficient for Q, right? So here is P, that's going to be our hypothesis, and getting a speeding ticket is Q, that's our conclusion. So this is the same thing as saying if P then Q. Okay. If I have the words necessary and sufficient, if I have both of them, then it's a biconditional in that case. Okay, and let's do one more. Let's say I tell you, whenever you get a speeding ticket, you are driving over 65 miles per hour. Okay, so again, you're driving over 65 miles per hour. That's P. You get a speeding ticket. That's Q. Okay, whenever we have the word whenever tells us that this is a conditional statement. That's also from the list of alternative ways to say a conditional statement. Okay, whatever comes after the word whenever is the hypothesis. So here Q is the hypothesis, P is the conclusion. So just like you said, this would be the statement if Q, then P. Okay. Any final questions on this? Yeah. Okay. I just from the list, so we had two questions. First of all, the word whenever, okay? Whenever you have the word whenever, it's a conditional statement. Whatever comes right immediately after the word whenever, that's the hypothesis of your sentence. That's the if part, okay? All right. And the other thing, everything else is the conclusion. All right. For a biconditional, let's say I gave you the sentence, you get a speeding ticket if and only if you're driving over 65 miles per hour, that would be biconditional. Or if I said you get a speeding ticket, let's say getting a speeding ticket is necessary and sufficient for driving over 65 miles per hour, something like that. Okay, or actually it would sound better if I reversed it. It means the same thing. Okay. Okay. 2 quick points before we finish for today. And all right. Point number 1: for biconditional statements, the order doesn't matter. All right. So P if and only if Q is the same thing as saying Q if and only if P. Okay. It doesn't matter which order you write it in. It's the same thing for conjunctions and disjunctions as well. Okay, the order does not matter. The order only really matters for conditional statements because there's a hypothesis and there's a conclusion. Okay. Number 2, if you're doing a truth table, let's say you've got 3 variables, P, Q, and R. Okay, you're going to need to put down every possible combinations of trues and falses. Okay, so you're going to have you'll have in a truth table with 3 variables, P, Q, R, you're going to have 8 entries. Okay, it's 2 to the power of 3. All right, when you had 2 variables, it was 2 squared, which is 4, right? They're going to be true, true, true. That will be the first row, and you go through all of them. Okay. How do you go through all of them in an orderly fashion? For P, you just do the first 4 being true, and then the last 4 being false. For the second one, Q, you do 2. You alternate by 2. So you do 2 true, 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 false, false, true, true, false, false. And for the last one, you alternate true and false, true, false, true, false, true, false, true, false. Okay, and that's how you get all 8 of them. Okay. Any final questions on this? Okay. Everyone, please just let me know you were here in the chat for the attendance. This recording will be up on Blackboard. I'll also post your first homework assignment on Blackboard as well. Okay. Once you've let me know you were here, you can head out, and I will see you guys on Wednesday. Okay. Have a good day, everybody. Okay, I assume that's it. Last call. Oh, okay. That's all right, as long as I knew you were here. Thank you.
Professor?
Yes, how are you?
Thank God, I'm good. What's the homework again?
Oh, I'll post it on Blackboard. It'll be up later.
Okay, thank you.
No problem. Okay, take care. Have a good day.